Hello and welcome to today's episode of the Teardown Sessions. I am your host, Helen Leigh, and today my guest is Dr. Andy Haas, who is the creator of a very cool open source USB oscilloscope, which we're going to be learning all about today. But before I bring on my guest, let me, as usual, let you know what's going on at Crowd Supply very quickly. So this is the Haasoscope Pro. It has just gone live, and the creator of this will be on to tell us about this very shortly. Also, we've got Pulverine at the moment, which is using, I believe, a Bosch sensor. Yes, a Bosch PM 2.5 sensor. So people are quite excited about this as well. So if this is your bag, go check it out. We've got a breadboard power supply that's compatible with USB-C. This is a lovely little device, actually, very simple, but people seem to like it. And that's crowdfunding now as well, a couple of weeks left if that seems like something you'd like to support. Open source, of course. Also going on at Crowd Supply are preparations for our annual conference, Teardown, which is based here in Portland, Oregon, in a semi-abandoned mall in what used to be a Gap. It's a really fun 300-person conference. Headliners this year are very exciting. We've got Cory Doctorow, Kate Stewart, who's head of embedded at Linux, and Benny Huang, who's obviously a very iconic and awesome hardware hacker. So as well as those authors, we've got a whole bunch of talks that are going live now, some really fun ones, chipperdoodles, hand-drawn circuits on keycard. That's a really fun one. Someone talking about crowdfunding from a non-English speaking language background. Alvaro, who runs the reverse engineering podcast, he's doing a really cool talk as well. Carrie Sandra, who many of you know and love, is doing another excellent talk about the woes of putting a battery in it this time. So I'm very excited. Lots of fun things. Call for proposals currently open. So if that sounds like fun and you've got a fun thing that you'd like to talk about, do a workshop about, do a hacker art installation, or have a table to demonstrate something, now is the time to get in touch. So yeah, there's tickets for sale as well, obviously. So that's what we got going on at Crowd Supply. So let's, without further ado, let's bring on the person you're all here to hear from. Oh, Greg's here. Oh, nice to see you, Greg from hello, Altara is here. Thank you for joining us and saying hello. Hi, lovely. Okay, let's bring on Andy. Andy, can you please say hi to everybody and introduce yourself and let everyone know what you're here to talk about?
Yeah, hi. So I'm Dr. Andy Haas, and I'm the creator of the Haasoscope and the Haasoscope Pro. And we're here to take a look at it and show you how awesome it is.
We are indeed. So where do you want to start, Andy? Would you like to give it? So is this what you do full time? Is this your job forever, or is this your side quest?
Not at all.
What's your background then? Where are you coming from? Why are you making a USB oscilloscope?
I don't know, but I'm a professor of physics. I'm here in my physics office at NYU. I do high energy particle physics, so I build experiments. I build parts of experiments that then get shipped out to CERN, and we install them at the Large Hadron Collider, which is the world's biggest particle collider. And yeah, I've spent my whole career doing that and looking for new particles. I was part of the team that found the Higgs-Boson in 2000.
You weren't. You were not.
Yeah, my name's on the paper.
Wow. We've got a genuine celebrity on the stream today. That's amazing.
I won 1/3000th of a Nobel Prize.
Listen, that's 1/3000th of a Nobel Prize, more than the vast majority of people will get in their lifetime. That's like, amazing.
Yeah.
So you're a particle physicist in real life. So, so you're just making hardware to challenge yourself in your off time. Is that right?
Yeah, it's really a hobby, but it's also helps my work a lot. We need a lot of high-speed stuff. We need a lot of data acquisition, and so learning how to build an oscilloscope is the best way to learn how to build all that other stuff. So it's helped my work tremendously.
Is that right?
Yeah.
And what, just because of the knowledge that you need to process that signal in the fastest way possible. You're learning how it's done, so you're learning better ways of working with it, right? How does that feed into the work?
You need to learn the whole ecosystem, right? I mean, from start to finish of the signal going in to analyzing the data coming out, from the firmware programming to the software and all the analog stuff, and everything. It's a lot of stuff that goes into a product like this, and learning all those little details, even just how do you solder a BGA, right? That's not something you learn doing physics, right?
It is not, no.
You find yourself in a tunnel at CERN and something's broken, you have the skills to use a hot air gun and fix that board and put it back downstairs. So just the whole range of skills that you need is just super important, and you learn everything by doing a project that you're responsible for the whole thing.
That's amazing. And is that something that happens often with your colleagues at CERN? Are they also interested in getting down to the nitty-gritty and understanding how every single aspect from the top to the bottom of that works?
Some probably are. I don't know any that have built like too many electronics products on their own. But you find a lot of open source products. And, I mean, the internet was invented at CERN, or HTML, right? So it's that kind of thing. It's the idea of inventing something new and then making it available for everyone for free. I mean,
it's really exciting.
Profit is kind of part of the philosophy also, and why we do it.
I've not been to CERN, but obviously CERN's becoming even more and more important in the open source hardware world. I mean, more and more I'm seeing, because outside of this side of things, I do all the intake, so all the projects that come through, they'll come through me initially, and I'm seeing more and more people adopting the CERN open hardware license, which is really cool. And of course, CERN was pivotal in making KiCad usable. I started trying to learn KiCad before CERN had their people work on it, and it was really difficult. So yeah, CERN's really been at the forefront of open hardware for many years now. So thank you all for your service. Yeah, that's really cool. I'm sorry, I'm supposed to be talking to you about your oscilloscope. I'm not meant to be fangirling about CERN.
That's totally fun. I'm happy to be a part of it. It's a great place.
Yeah, it really is a genuinely cool place. I would love to go one day. So let's talk about Haasoscope, the original one. You said you set out. I mean, looks like a very different device to this device. I mean, but you did well. You raised over 30K for it, and you've obviously made a huge amount of progress. So take me through what it was like building this, and then moving on to something that's more productized like this. This looks very smart, by the way. You've done a good job.
Thank you. Yeah, no, I mean, if you go back to the original, I mean, that looks like kind of the first project that somebody has ever done in electronics. And it really was one of my first projects in electronics. That was me learning electronics and soldering, and I'd really never done much of any of that before. This was 8 years ago, and I wanted to learn it. I just fell in love with doing it. It's so cool to
it is, agreed,
read the data sheets, and you can just design a board on the computer and put the parts on, and it does something amazing and does what you want it to do. And I love the problem solving of figuring out why it doesn't work, which most of the time it doesn't. And that's how you learn, and it's just really fun to solve those problems one after another until eventually it does work, and you can get it to do so many cool things.
Yeah, agreed.
So, yeah, this was the first. My goal was that there really was no open source oscilloscope, and it also was a way for us to record data. So I needed something that could was cheap, and you could plug into something in your lab. You could buy something for like $2,000 that would 500 megasamples per second, and I don't want to name names, but plenty of professional companies will make that kind of thing and let you save the data in some weird format, and you have to go figure it out. It's not very flexible. It takes a while to learn their ecosystem, and it's expensive, right? So this is something I wanted to build that you could just plug it in. It's simple, and it works, and you can change it if you want to. You can change the firmware. You can design new triggers. You can make it save to a CSV file if you want, and it works great. And we actually use them still for some experiments that are running at CERN today. They're sitting there taking data, and still going.
That's really awesome. Many years later. Was that 2017? That's a few minutes ago.
2017, yeah. So it's way back.
We got hello in from Germany, Sol Hubner. Sorry if I've destroyed your name there. And he said that I really like that you can cascade it. Can you explain what Sol means here?
Yeah, so if you see these headers sticking out to the left, and then there's one sticking out to the right that's plugged into that Raspberry Pi, you can take multiple ones and you can plug them together side by side, and you can turn 4 channels into 8 or 12.
Oh, interesting.
I've got one experiment now on one of my experiments that I think it's 12 or 16 boards plugged together side by side, and it's a long row. I think it's 48 or 68 channels, and that's something.
68 channels. Oh my word! I think that's the most I've ever heard of.
4-channel oscilloscope, right? But in physics, we have all the time. You have tons of channels from tons of detectors, and you need to record them all simultaneously. And so that's a use case that it's not actually that rare, I think. It's not just physics. You have lots of channels you need to record, and that's a nice way you can do it.
Speaking of use cases, and I normally sometimes ask my colleagues like Crowd Supply if they've got any questions for people, and one of my colleagues who is definitely more of a software person than a hardware person wanted to know, like, what do you use oscilloscopes for? Like, what are the different tasks that, because I'm guessing, like an electronics engineer might have a slightly different answer from you as a physicist, but I think it would be interesting to go over some use cases, some interesting use cases of the Haasoscope and the Haasoscope Pro, like the actual tasks that you might use it for.
Yeah, well, I mean, look, the oscilloscope is one of the most basic electronic instruments that you have, probably after the multimeter, which measures voltage and current. As soon as you want to see something changing in time, right? Like you have a signal which is going up and down, like maybe it's an audio signal, right? That's playing music or something. Well, if you want to see that electrical signal, a multimeter is not going to help you. You'll just see like the average voltage. So the oscilloscope lets you see the voltage as a function of time on a graph, and then you can take an FFT of that. You can see what signals, frequencies are present as a function of time. You can, debug what's happening. Like maybe you have a serial bus or something like that. Then you need to see the data flowing on that serial bus, and you see that, oh my, SCL line is not a square like it should be. It's actually got some capacitance, so it has some weird shape, and that's why my serial bus isn't working. So it's for debugging and understanding and fixing electronics. You need an oscilloscope if you want to.
You do.
Fix some broken piece of electronics. So yeah, I mean it's everywhere. Now,
it's a multi-tool for debugging for hardware, that's for sure.
Right.
And where does the processing happen on your device? Are you doing it on device, or are you just collecting the signals and your computer is doing the processing of the signals?
Some of both. So
okay.
It's a pretty typical oscilloscope design. You've got you can kind of see buried under the little silly screen here.
Let me put it on.
There's an FPGA under there.
What I was going to say, yeah. Tell me, yeah. Which FPGA have you gone for?
well, so this is the original Haasoscope. This was a Max 10 Altera
Oh
device.
wow. Yeah. Here we go.
So yeah,
Let's see if we
there's
can get
the FPGA.
there. Yeah.
And it's doing the triggering. So it's taking, here's the ADCs in the front next to the BNC connectors. And those are feeding data in real time to the FPGA. So the FPGA gets all the data, every single sample. And then it processes the data. It's triggers, it says, is something interesting happening? Like, did this signal go high very quickly? Is there an edge? Or is there, some more complicated signal that you want to trigger on? When you trigger, then it stores that that data into its memory, right? And then it waits to be read out by the computer. So that's a pretty typical, only the FPGA can handle that rate of information,
Yeah.
doing something very fancy and doing
Of course.
everything on the computer. But basically that's the simplest and cheapest way of doing it. FPGAs are great at processing, a huge rate of information. So in the Haasoscope Pro,
yeah, I was going to ask, like, let's switch over. So, and then in this new edition, how has that changed, or is that the same?
In the new one, I think we have a picture of the board down there too, maybe.
There's the Pro.
Or look at the routing.
There's
you have the routing.
You mean this one? Do you mean this layout?
Yeah, I mean, that kind of shows you where the information is going. So you've got the two front ends on the left again. So there's two channels on the Haasoscope Pro. It's not those. Those are actually USB.
Oh, these two. Oh yeah, I see. I haven't got my glasses on.
It's these little green circles at the top. Those are the BNC connectors.
Oh, I see. Yeah. I see them.
Yeah. So all that data comes through these analog front end chains. You have these relays here, which can, go to 50 ohm or 1 mega ohm impedance and things like that. But the FPGA is this. Well, the ADC is this littler square on the left with a lot of wires, and then the FPGA is this
thing. That's ADC FPGA.
Exactly.
I don't know if you can see my mouse.
Yeah, I can see it.
Okay.
So that ADC is putting out 56 channels of LVDS data at 800 megabits per second. That's how we get the 3.2 gigasamples per second at 12 bits per sample. It's something like 48 gigabits per second or something ridiculous like that the FPGA is processing in real time and then making decisions on whether to trigger or not and storing the data in a buffer to be read out. So it's really, we're like maxing out what this Altera FPGA can do. It's really amazing.
Yeah.
But then that's it. Then once it has the data stored after a trigger, then it gets shot out the back over USB-C to a computer, and there we just have some Python software, which is really nice, easy to understand. Python, open source.
Is that your software, or is that something that you've made your device compatible with?
Yeah, it's just a custom Python software. I took the old Haasoscope software and I, ripped it apart basically down to, just kept the part that's like doing the data communication basically, because that all should be the same.
Mm-hmm.
But everything else is kind of new. It's still Qt and Python, so that's what we use for the GUI. It's all a Qt Python interface. So
everyone uses Python these days. It's just
so
everyone.
easy to, I was adding an FFT to the, I wanted to take an FFT of the data coming in and have an FFT plot. It was like 3 lines of code, right? It's just so easy to do things in Python. Or I wanted to resample the data and add, data points along the way. We usually do sin x on x resampling for oscilloscope data. So
you can do some wild stuff with Python these days. You can even do Python-based FPGA scripting, which is wild. Amaranth, I think, is what they call it. Anyway, there's all sorts of really cool permutations of Python that people are using to do really complex things. Talking of things, I've got a question from Greg Stiert from Altera saying, does it work with SIGROC?
No, not at the moment. So yeah, SIGROC is, as far as I understand, it's another oscilloscope software interface that a few other scopes use, and I think people have written like drivers for them that you can then use that to communicate even with like benchtop oscilloscopes and things like that. So I mean, it certainly could be done, right? I mean, you have all the data coming into Python on your computer. You just need the part that would communicate that to SIGROC, and you know, but I'm not a SIGROC expert or anything like that. So I think that would be hard. Somebody was working on that for the original Haasoscope.
What, someone in your community?
I think they lost interest or something. So it could definitely happen, but you know, not at the moment. Following
on from that, I think a good question from Dimitri saying, is there a CPI API to this oscilloscope?
No, there's not that either. So that, if people don't know, that's kind of a standard kind of old-fashioned serial language that you can use for remotely controlling your oscilloscope, like from your computer or something. This is already all on your computer, though. It's, you know, if you want to do something remote, then, you know, you could just DNC into your computer or something like that and have the oscilloscope up on your computer screen. So kind of already is a remote connection. So, I mean, again, you could certainly add that pretty easily, I'm sure.
There's a related question about the API. So it's not a question, it's a suggestion saying having a nice API could allow integration with all these things that we're talking about. Is there something like that in plan? Are you, maybe somebody in the community might be interested in helping bring that functionality?
Yeah, definitely. Cool. I mean, I've tried. You know, I encourage people to take a look on GitHub. It's pretty simple code. You know, the data comes in, it's in a class, and it's only like 5 or 6 Python files. I think my code is easy to understand, but most people probably think their code is easy to understand. So yeah,
I don't.
Software, you've got all the code there. So I don't pretend to be the world's best coder or anything like that. I think, you know, I keep it simple though. So at least it's not too complicated to wrap your head around. Like, you can find out what's going on.
Listen, you're a particle physicist who makes oscilloscopes for fun. If you were the world's best coder, I think we'd all be very upset.
Yeah,
you have to have some kind of gap in your skill set. Leave some for the rest of us. But yeah, if anyone would like to chip in on that, please, the GitHub is right there. And I know that a lot of people in the open oscilloscope community have contributed a lot of code. Thunderscope, Alexa from Thunderscope has had a lot of contributions to the community. I know that for sure. So please do get involved. Henry Haas has said he loves that he's open source. Of course, we love it too. And what would you expect from technology from CERN?
Well, you noticed the last name on that person.
I did notice the last name. It's some kind of definitely very rare.
Shout out to Henry. He also made the amazing video that you see at the top of the crowdsource.
Oh really?
Crowdfunding page. So he's great with that.
That's delightful. Simon saying there's a nice open scope is always welcome. Okay, I'll go back to some of these comments again later, but why don't we take, because I know that you've got some live demos that you'd like to do. I've shown people where your GitHub is. Do you think it's a good time to take a look at your
Sure.
I'll come back to some of the other questions in a moment.
We can definitely do that. Yeah, I have things kind of up and running here. So yeah,
shall I just bring it up?
Yeah, you can bring it up.
Let me do it. Let me show. So we're going to do a live demo on the live stream.
It's always a little bit dangerous.
Let's move us down. I'll move us down so we can see the full full screen.
Sure. So, you know, the software is kind of a work in progress here, but you've got the basic
Always.
oscilloscope interface here. You know, you can change the gain. You've got your offset. You can turn channels on and off. You can change the triggering and all that fun stuff. But you know what's amazing about the Haasoscope Pro is just how fast it is, basically.
Yeah.
So what I have plugged in here at the moment is I can just turn off the other channel, since we'll just look at one, for instance. But just on a single channel, what you can see is you can zoom in faster and slower. So, you know, we'll just look at how fast it is. So just pausing for a second. You know, the scale here down at the bottom, this is 2 nanoseconds, or, you know, here we're 1 nanosecond per division. These are the individual samples, which you can see here. So we've got a little over 3 samples per nanosecond, and you know, the bandwidth is just incredible. So you can get rise times here of you know, just with a single channel, single Haasoscope, the rise time is well less than a nanosecond. It's something like 300 picoseconds. And
Right.
we can talk about it later, but you can also put 2 Haasoscopes together, a Haasoscope, and you can oversample, so you can get a little over 6, so 6.4 gigasamples per second, and then you can get rise times down around 200 picoseconds.
Yeah, we do actually. Well, there was a question in the comments about sample rate and speed and how you might measure it. I think there was the sampling rate was 3.2, but you just said it was 6.4. Can we take a minute to explain how we measure the speed of an oscilloscope, like, and what, like, in because is it the megahertz, is it the, you know, what's
So I guess there's 2 things, right? The first one is just the sample rate, so it's how many times each second you're measuring the voltage, right? So in 1 second, we're measuring it 3.2 billion times, right? That means you have a little over 3 samples, 3 measurements, or 3 data points here of the voltage in each billionth of a second, in each nanosecond. So you need a fast sample rate in order to see fast changing signals, basically. The other important criteria is bandwidth. Bandwidth is more of an analog thing. It's what range of frequencies you're able to see without it being suppressed, right? There's always, if you have capacitance and things like that, then high frequencies get suppressed. So you also need incredible bandwidth. Otherwise, even if you had a fast sample rate, this whole thing would be really spread out, right? So you'd see lots of dots, but you wouldn't see a sharp rising edge. You'd see a smoother curve, which is, you know, not what's really there.
That's interesting. Thank you for explaining how those 2 numbers are required. Okay, carry on.
Yeah, okay. So let's see, I guess I could actually try to show the oversampling here. So if we start running again, I can leave that on. I'll turn it off. It's a little faster drawing. So if I turn back on the other channel, let me go slower for a sec. You'll see they're actually synced up. So what I have here, you can't see on my desk, but I've got 2 Haasoscopes plugged together, and there's just an Ethernet cable that goes
I'm just gonna spotlight you so we can
Okay.
see you. Like, there we are. Go on, show you.
Each Haasoscope Pro has an Ethernet cable connection. It's not Ethernet, it's just an Ethernet cable, which we're using as an LVDS cable for wires, basically. But it's a really great way to send just signals with very fast rise time. We just talked about rise time bandwidth. So Ethernet cables have fantastic bandwidth, better than a gigahertz even. So we're just using that cable, and you can plug from one Haasoscope from the out to the in of the other one, and then that's how you sync them up. And then you also need the analog signal on the front, so you plug your signal in here from your device under test, and then it gets split out here, and then you can plug that into the second Haasoscope. So that's how you connect two of them.
Very cool.
You can see that it's measuring the same signal, right? They're like,
and that's what we're looking at right here.
Yeah, they're totally synced up. And I almost have it working. It might work here, it might not. Do the auto calibration. No, it didn't quite work. But once you line them up in time, then you want to line them up precisely, right? And then once they're lined up precisely, then you put them together into a single signal, right? So now you're sampling, and now you have, when you look at it, if we zoom in there, we're going to see that we have, not just, this is 1 nanosecond still per division here.
Yeah.
And now you see we have 1, 2, 3, 4, 5, more than 6 samples per nanosecond. So we're getting that 6.4 gigasamples per second. This looks a little wonky because I didn't do a great job of lining up the signals. We can make that a little bit better. And so what I'm adjusting here is the fine delay. There's 2 things you need to adjust here. One is you need to adjust how many samples offset there is between the 2 scopes, like how many, just moving whole samples, whole dots, right, left or right. The other is a finer adjustment, which you do by talking to the ADC and saying, don't sample right now, like sample 30 picoseconds later. That's what you can do with this fine delay, and that's how you make it, really good. So there's an auto calibration procedure that you can do by plugging in a cable from the back to the front and doing auto calibrate. Doesn't work with every signal, so you need like a signal with a rise time that is appropriate so that it can detect the offsets, right? So if we'd done that, then it would auto calibrate it. But right here, I just did it kind of by hand, but it's pretty easy to do, as you see.
Yeah, very cool. Once you've been collecting the data from your measurements, what do you like? How do you get that data? Like, what do you do with that data? Can you collect previous measurements? Does it like save it to your computer? Like, how do you work with the data? Do you have to export it, or?
So I mean, usually when you're using an oscilloscope, you're just looking at the data on the screen, like
just live.
You just want to, you just want to see it, what the signal looks like, and maybe you want to measure things about the signal. So maybe you want to measure the RMS of the signal. So there's measurements over here on the right, which there's kind of limited things, but you've got the basics, you've got the RMS and the mean. You can measure frequency, you can measure the period of the signal.
So this is the stuff that you're doing when you've actually got your device hooked up.
Yeah.
This is the live analysis. Yeah, that's cool. But is there, there was a question from the audience saying, is there a way to get that data to analyze previous measurements?
Yeah. So you can also save all the data to the file. So this record to file button, you can just save all the data.
Oh, I see at the top, yeah.
a file, and there's a couple different formats supported. So yeah, I mean, when we're using this at CERN, right, we're not just like throwing the data away. We want to record the data that's been taken. So you definitely can record all of this information to a file, and or you could process it and just save some events to a file. Whatever you want to do.
Very cool. I've got a bunch more questions as well coming through. So someone called Brewster Lamacchia, thank you for joining us, Brewster. Could this be used for a crude PCB TDR impedance measurement? Could the LVDS port on your box create the needed fast rise time pulse?
Not quite. So the rise time of the on the LVDS port is just the rise time of the FPGA output, which is it's about half a nanosecond, which is, I mean, that's pretty fast, but it's not really that fast when you have 6.4 gigasamples per second. So yeah, what this signal is actually a 10 megahertz square wave from this famous Leo Bodner pulse generator, and this has a rise time of 30 or 40 picoseconds. So yeah, it's not. You'd still need some external pulse generator to do a TDR measurement.
Nice. All right, we've got on for another question. Someone called Dimitri saying, I would be interested in developing better Python API for this. Is there a developer program for your board? I know some people do it. And if so, how do people get in touch with you? Would it be through GitHub, through CrowdSupply, whatever?
Yeah, you can write me a question through CrowdSupply. You can write me on GitHub. I'm pretty easy to find. My email address is also on my website, drandyhaas.com.
There's the GitHub up on stage as well, so you can see the GitHub handle right there.
Just Google Dr. Andy Haas, and I should show up there somewhere.
Yeah, we got a website for you somewhere, haven't we?
That's fantastic, Dimitri. Anyone that wants to help develop this, I could definitely test out your code, or send you a loaner or something like that. So I have plenty of kind of older beta models which are just sitting in my office collecting dust. So happy to share them.
Awesome, that's great. And this is the website, drandyhaas.com. It's got a little contact as well. So anybody who's, I mean, we see that a lot. I mean, my friend Tim, who made the what was his little board? Tim Ansell, who made, is it the FOMU, his first one? Anyway, I don't remember. Anyway, he said that he the only reason he makes open source hardware is because he hates to code and he wants other people to go and help him out on his GitHub. So I do think that there's a lot of love from the open source software community coming through to the open source hardware community. So I hope you do find some contributors who are willing to help you. That'd be cool. All right, let's go to this one. We've got a question. Micro Sparky. Hi there, Micro Sparky. Thanks for joining us. We've got, he said, 2 gigahertz bandwidth is a super ambitious goal. It's true. What are some of the challenges with the front end layout and materials needed to achieve that? Good question. Thank you for asking it, Micro Sparky.
Yeah. Well, I'd say it's interesting. I also expected it to be extremely hard, but in the end, there were amazingly few challenges. So,
oh, really?
A standard FR4 board works fine. No problem. I have signals which can go even 3-4 inches, and there's maybe only a decibel of loss. So you don't need like Rogers material or anything like that. The front end also amazingly easy. The only thing is you need to buy really nice components. So
can you expand a little bit more on that?
Yeah, so I mean, this whole design, full disclosure, is 100% based on the Texas Instruments reference design for this ADC. And if you look at the data sheet for this ADC, and they also have other application notes which just tell you what chips you need to put together. So you've got a fantastic LMH5401, which takes the single-ended signal and turns it into a differential signal, and it has a bandwidth of I don't know, like 8 gigahertz or something ridiculous. And then you have a variable gain amplifier, the LMH6401, and takes that differential signal and does all of the amplification. And then that goes into the ADC, and that's kind of all you need to do. The only tricky part actually was the stuff just before that. So these red blobs, these relays, you just have to be careful when you're at these frequencies. So, and you have to really test things. Like I bought relays that said they worked to 2 gigahertz. They didn't work to 2 gigahertz. They worked to maybe 1 gigahertz. So I had to get, a different relay that said it worked to 3 gigahertz, and it works to like almost 3 gigahertz. But these relays are like $10 each. Things are not cheap when you.
They are not. That is not cheap. That is not a cheap relay.
Things on this board are, I mean, look, things are not thousands of dollars, but things are more expensive. You need components which are designed to work at these kind of frequencies. You have to be even careful. Like I did run into problems with a capacitor. I made the board and they threw on some random capacitor, which was supposed to be 1 picofarad. And maybe it is 1 picofarad, but it's not 1 picofarad at 2 gigahertz. And so you have to be careful about what capacitor you use. So I use only one brand. It's all Murata capacitors, which I've tried out, on all of the important high bandwidth signals. So, little things here and there created challenges, but basically it's a standard kind of board, like you would make. I mean, it is a 10-layer board. The real challenge was, if you look at this picture, the real challenge is look at all those wires. The ADC and the FPGA.
That's a lot of routing.
What took me, a long time to figure out, and doing that without any fancy PCB assembly techniques with you don't want blind or buried vias.
No, of course not.
That costs, thousands.
Yeah.
Right off the bat.
Yeah, absolutely. So did you say it was 10 layers, your PCB?
10 layers, yeah. The reference design uses 12 layers. I got it down to 10 layers.
Wow, a minimalist.
Yeah. Yeah.
Wild, very cool.
I mean, I'm also making a 24-layer board for some work stuff. So it's not such a big, it's actually not that expensive to make. A 10-layer board is like $100 versus, a 4-layer board is $20 or something. So it's expensive, but it's not that expensive.
Yeah. Things are much less. Okay, thank you for the in-depth discussion of the challenges you found with the components. That was super interesting.
Yeah, I have a Hackaday page where you can it's linked from the GitHub.
Oh, really?
And yeah, I wrote quite a number of
Let me meet myself and find it.
Where you can read about some of my struggles with some of these fun things. Yeah, I'll just talk. One of the other challenges that I didn't mention was doing the anti-alias filter for. So what is an anti-alias filter? When you have a signal coming in, it may have higher frequencies than your ADC is able to sample. So if your ADC is sampling, let's say 1 billion times a second, well, clearly you can't see a 1 gigahertz signal if you're only sampling 1 billion times per second, because you'd have one sample for every cycle of the wave, and that's just not enough information, right? So there's this Nyquist thing, and you don't want frequencies coming into your ADC that are above half the sampling rate. So at 3.2 gigasamples per second, you don't want frequencies going in that are more than 1.6 gigahertz. So you need an analog filter before your ADC that's able to cut out those higher frequencies. But doing that on the board was definitely a challenge, because you're working, the component values that you need are like a few nanohenries and like less than a picofarad, and just the parasitic capacitances on the board and things like that are of that same scale. And so it took a lot of hand tuning. Like I have a book of capacitors, you know, of all sorts of different values, and you have to like try one and like, oh no, that doesn't look quite right, and then you get back and then try another one. I'd say I spent like 2 or 3 days just, you know, fine tuning those capacitor and inductor values for that particular, you know, board, 10-layer board. And you know, but it works now. But that was definitely a challenge dealing with these high frequencies. You have to worry about.
I did find your Hackaday project. Is this what you're talking about here? The
Yeah,
Haasoscope
totally.
Pro logs.
Yeah, well, there's the anti-aliasing one. Yeah.
Yeah, here we go. Yeah, that's very in depth. So if you want to read more about what Andy was just talking about, I put the link just in the chat, and we'll put it in the show notes at the end as well, because this looks great. Look at that, lovely.
Yep. Yep.
All right, let me go back to your. There we go. You can carry on. And this is the URL where you can find that build log with the anti-aliasing post as well. So.
Yeah, I forget what other ones I wrote there, but you know, whenever
I interesting looking ones, yeah.
I tried to document some things. You know, it kind of documented some of the works in progress, which are fun. Well, there I am tuning another thing, which is that in order to combine this analog signal between a lot of work went into how do you combine two Haasoscopes together and oversampling. It's, you know, just getting that matching to work of the impedances. I have to use a lot of fancy words, sorry. But, you know, getting that impedance controlled when you're going outside the board through connectors, through a cable, and then hitting another channel, you know, there's losses along the way, right? So if you want the two signals to be the same, right, you have to compensate for those losses somehow so that you can then combine them. And, you know, you have to tune those frequencies of compensation so that can actually work.
Very cool. Yeah, there's the oversampling. Really great blog posts here, Andy. Overview of the firmware. You've got.
Yeah, I talked about how the firmware works.
Here we are. This is the syncing units post. This is the one. I know people will be interested in that one. There we go. That's cool.
Yeah, there's some details there about the LVDS signal.
I was going to ask you about this. Yeah, you've gone for an extruded aluminium, or aluminum, as you say, I guess.
Yeah, I mean, it's actually doing something. So I spent a bunch of work on that too.
Nice.
Like, the other problem with 2 gigahertz is radio waves, right? I'm sitting here in New York City, and you know, there's just tons of radio signals. In fact, this is kind of fun. Let's see if I can get this working in real time. So I'll start this up again. I'll just go to the other channel. So I'll turn off the oversampling. And oh, I guess I haven't shown the FFT yet at all. So let me just show that real quick too. So we look at an FFT of like the second channel here. And I need to trigger on it so it doesn't look so wonky. So check this out. So this is an FFT. I'm going from 0 to 1.6 gigahertz, right? You notice these noisy things here. This channel, by the way, just has a probe plugged into it, and the probe is just sitting there doing nothing.
It's just dangling around.
it's dangling around.
Yeah.
But so what is this noise? Well, we can go slower so we can see it. And look at this, 100 megahertz. So in the US, right, this is FM radio. I can make this bigger, sorry.
Oh, I'm a little owl. Sorry, I have to peer at the screen to see what's going on. All right, cool.
Oh, we can also do this. So we can also increase the memory depth, right? Before I was doing just well, it was like 4,000 samples. This will be something like 40,000 samples, just so we can get some more resolution on the FFT.
Wow.
When you take more samples, then your FFT has more resolution. So here's your FM radio noise, right?
Yep. There it is.
And you have like, I think this is television or something, and there's tons of noise. But one reason we're seeing that is because this board is just sitting out like on my desk. It's not in the case, right? So when you put one in the case, then that's how you're getting rid of all that. And
You're shielding it.
Obviously the aluminum enclosure is important, but you also need the front and back panels to be grounded, right? So
you're just using PCB panels, right? Or
yeah,
you
PCBs.
Yeah.
But you need the ground planes on the panels so that those are grounded, and you need the screws here to be grounded and make a grounded connection to the rest of the case, right? And there's actually some grounding here too. So you need no gap anywhere that is more than like a few centimeters if you want to keep out.
Yeah. Something I had not considered, to be honest. This is a good point. I can't believe we've not brought it up until now. But let's talk about probes.
Yeah.
We've got a couple of questions. What about the active probe? Yes.
Right.
What about the active probe? Would love to talk about that. And then also, Francisco also said, or a current probe. Any recommendations? So let's take some moments here. Let's talk about probes. Have you got any on your desk? You probably do as well.
Yeah. Here's the active probe. So
let me full screen you. There we go.
Wait, so I'll actually just unplug it so we can see a little better. So it's pretty small, but if
you put your hand in front of it, the cam in front. Yeah, that's it. Put it forward. The camera will. There we go. It's a beauty blogger trick. Look,
okay.
Yeah, it's focused because otherwise it tries to focus on your face, right?
Okay.
Now you can see. You can actually see the parts on it.
I can take off its little.
Take off the shell.
So yeah.
There we go. Yeah, we can.
It's a pretty simple design, but again, a lot of why doesn't that?
Some cameras are better at it than others. I focused a moment ago.
A lot of analog work went into this. So this is a wonderful design, not by me, but by James Wilson. And actually, it's interesting that the probe came first. James put up this Hackaday post. Well, he made a wonderful web page explaining this probe and how it works, and that's also linked from my GitHub page. It's a 2 gigahertz active probe, and it's using the same kind of idea, just basic 4-layer board, wonderful Texas Instrument components that make this possible, and some really nice work, tuning all the little capacitors and analog signal chain before the buffer amplifier. But it works. It's amazing. And I saw that and I said, wow, you mean I can have a 2 gigahertz active probe? I don't have a 2 gigahertz oscilloscope, right? I mean, I could borrow one from somebody else in the physics department, but I don't.
Or you could just build your own, Andy. Don't be lazy.
Got to build your own stuff. So, I mean, if you can build, but that kind of sparks my brain, right?
If you can
build the probe, then can't you build the scope to see the signals from the probe? I mean, that means that it's possible to do the analog signal processing, inexpensively. So all that you need is a fast ADC on the other end of this, and you should be good to go. So a year later or so, then here we are. We have the Haasoscope Pro. So
So you're using that specific probe, also open source. That's really dope. Love to hear it.
Yep, totally open source.
I've got another question from Greg saying, does the power quality, trying to get sentences out of my mouth, does the quality of the power supply affect the probe or scope? Good question, Greg.
Yeah, no, it doesn't really.
Oh.
I mean, so both on the probe, and if you read James's webpage, he goes into a little bit of detail on this. So he's been very careful to, trying to take it apart again. He's been very careful to keep the, power comes in, it's just 12-volt power, but there's all this power section before, which is all linear and, is able to make plus and minus voltages. And he's got some nice capacitors on there. And he's got some really good, again, fantastic Texas Instrument power regulation that just makes really clean power for the rest of the important chips. There's really only 2 other chips on here. There's 2 other high-speed operational amplifiers that work in tandem to have good bandwidth and offset properties. But yeah, no, the power is, I'm just putting in, crappy USB power, in 12 volts, and it's really no problem. So it's down like 80 decibels by the time it gets to the front end. So that's fantastic. And then on the I have to unplug it. Well, I'll show you the old version, but we have this whole half of the board is all power, right? This is all the power regulation. So everything has, there is switching all the way back here, but it's way back here, and then it goes through linear regulators, and it goes through filters, and it goes through capacitors. And the new version of the board actually has a 1 millifarad capacitor for each of these, just to reduce the switching noise even further. So, I mean, there is a tiny bit of switching noise that you can see around 100 kilohertz. I mean, you can never get rid of all of it, right? But using USB-C power is no problem for the Haasoscope Pro.
Very cool. All right, well, we've been somehow speaking for an entire hour at this point. We're right at the end, so I'm going to go back to my to your campaign, just so everybody knows where to find it. It's just gone live, right? Did it go live yesterday, I believe?
Yeah, just 2 days ago.
So we've just gone live. We've got 42 days left. So if you want to support Andy in this venture of extremely fast open source USB oscilloscopes, now is the time. And you can support either by buying one, obviously, having your own, or you can head along to Andy's GitHub or Andy's Hackaday page or the Crowd Supply campaign, and to get involved with helping with some code for it would be great. Also, I wanted to give a quick shout out to the sponsors of today's stream and the sponsors of the program that Andy is part of, which is Altera's Innovation Lab, who are doing some really cool stuff with Altera FPGAs. So we do have a supplier program that we do all sorts of cool things, and Andy's part of the program here, so shout out to them. Thank you. And I know that Greg is here from Altera as well, so shout out to Greg as well. If you're interested in hearing a little bit more about that, you can look back in time, and there's a couple of sessions ago I did actually have Greg on the stream to find out what they're doing at Altera, so do take a look at that. But apart from that, please do check out Andy's website and get involved on GitHub. Take a look at the campaign. Is there anything else you would like to say to the folks at home before we sign off, Andy? Oh wait, I've got another question that we didn't answer. Wait, let's do. You got time for one last question?
Sure.
All right, here we are. I think I got everyone else's though. Dimitri says, are there any functions that compute inside of scope FPGA, like let's say a signal primary frequency, duty cycle for PWM signal, and so on? Or would that have to happen outside of the scope?
You know, for things like that, it's so fast to just do them on the computer in Python, that I haven't found it necessary to put those in the firmware. So I mean, even that whole FFT, right, is happening in real time in Python, and it didn't slow down anything at all, right? So yeah, no, but I guess I would mention one important thing that is happening in the FPGA as far as computing, which is the averaging of signals. So that's actually really important. I should have demonstrated that, but
yeah, we can stay on for a little longer if you wish to say.
1 second, I still have it up here. This is
do it. You can do it. We can do it.
So
it's within our power.
Running fast, you see a little bit of noise here, right? I mean, I can even like zoom in, and we can see, you know, the level of noise, right? There's always a little bit of noise. I'm like zoomed all the way in. But if you go slower, right, then you can take adjacent samples and average them together, and then reduce the noise. Because the more you average, the more you reduce the noise, right? So all of that happens in the firmware. And when you go slower, I mean, the noise just disappears. We're still going, you know, this is like 10 milliseconds now, and you're down to what is this? You know, microvolts of noise, right? It's just incredible. I mean, if I zoom back out, I mean, there's no noise anymore. That's because we're taking all these samples and using the FPGA to average them all together and just read out the final result. So that's the main thing that the FPGA is computing.
Very cool. And we did have one final question that came in, which is similar. Just what about triggering? Is that in the software too?
Triggering is in firmware because, you know, only the FPGA has the data, all of the data. So only the FPGA can do the triggering. So at the moment we've got, you know, rising edge, falling edge trigger, but you can always add more triggers. It's got all of the data coming in.
Very cool. All right, we've managed to answer all of the questions. I think I got to everybody. Thank you, everybody, so much for joining us and asking your questions to Dr. Andy Haas. It does always make us feel less alone, and we do like talking to people on stream. So thank you very much for your interesting questions and for keeping us company. And a huge shout out to Dr. Andy Haas for joining us. I hope your campaign goes smoothly and is just as successful as your last one. I'm sure it will be. It's been a delight to talk with you, and thank you for your contributions to open source hardware and also, you know, physics in general. It's been a delight to talk to you. Genuinely, a really nice, really enjoyed chatting with you. So I will bid you adieu. I don't know when my next stream will be because I am in the process of moving workshops. So this will be it for probably a month or so, and I will be in touch. I'll announce on the YouTube next time we are doing a stream. But thanks everybody for joining us, especially Andy. I will see you again soon. Bye.
Thank you.
Oh, thank you.